All right, let's get into it. Today, we're basically opening up a cosmic cold case. We're playing detective, hunting down a fugitive that's been on the run for, about 3 million years. Our suspect is this bizarre collapsed star, and honestly, the clues it's leaving behind are challenging everything we thought we knew.
So to really understand our fugitive, we first have to visit the crime scene, right? The explosive death of a massive star. See, when a star way bigger than our sun runs out of fuel, it collapses and then just detonates in this spectacular explosion called a supernova. But what's left behind in all that chaos? Well, what's left is one of the weirdest things in the entire universe, a pulsar. It's the crushed, spinning core of that dead star. Imagine something the size of a city that's so dense, a single teaspoon of it would weigh billions of tons. And as it spins, it shoots out these beams of radiation. If we happen to be in the path of one of those beams, we see a pulse of light, just like a ship seeing the sweep of a cosmic lighthouse.
And the pulsar at the very center of our investigation today is known by its catalog number, PSR B1929+10. And this is not just any old pulsar. No, this one has a story, a really mysterious past, and it's leaving a trail of evidence that has astronomers just completely scratching their heads.
So, where is our fugitive hiding? Well, it's not really hiding at all. In cosmic terms, it's practically in our backyard. The distance is measured at 361 parsecs. That's just a little over 1,100 light-years away. That makes it one of the closest pulsars to Earth. And that closeness, that's exactly why we can study it in such incredible detail. And this thing is moving. It is screaming through space at 177 kilometers per second. That is fast enough to get you from New York to Los Angeles in about 22 seconds. This incredible speed is a huge part of its story. It's a runaway, a true cosmic fugitive.
And yeah, it's been on the run for a very long time. With an estimated age of about 3 million years, this is a very, very cold case. But thanks to some new evidence, we're finally starting to piece together its past.
Every good investigation has to start at the beginning. So our first clue is all about figuring out where this thing even came from. To solve the case, we have to rewind the clock by 3 million years and find the scene of the crime. The leading theory is that our pulsar wasn't born alone. It was probably part of a pair, a binary star system. Then, its partner star went supernova. The force of that blast was just so immense that it shattered their gravitational bond and launched our pulsar into space like a cosmic cannonball.
But here's where it gets a little tricky. By tracing the pulsar's path backwards through time, astronomers have come up with 2 different potential origin scenarios, involving 2 different possible former partners. So, was it paired up with the star Zeta Ophiuchi? Or was it a different star, one called HIP 86768?
To figure this out, scientists ran millions of computer simulations, basically tracing the pulsar's path over and over. And the results give the Zeta Ophiuchi theory a 2.5% chance of being right, compared to just 0.8% for the other star. That seems like a clear winner, doesn't it? Well, not so fast. There's a critical piece of data missing: the pulsar's radial velocity. That's the speed at which it's moving either directly toward us or away from us. We can only see it moving side to side. Without that missing third dimension of movement, we just can't definitively close this part of the case. Okay, so the origin story is murky, but our fugitive is leaving a trail of evidence right now. So let's look at our second clue, this massive glowing wake it's leaving as it plows through all the gas out there in space. Using some really deep observations from the XMM Newton Space Telescope, scientists found that its X-ray trail is just enormous. It's about 8 arc-minutes long. Now, to give you some perspective, the full moon is about 30 arc-minutes across. So this glowing scar in space is more than a quarter of the width of the full moon, and it's twice as long as we thought it was.
But there's more to this trail than just its size. This deep X-ray image revealed some new, totally unexpected structures. We can see the long axial trail streaming right behind it, but now we can also see 2 fainter lateral outflows branching off to the sides. And, most curious of all, something really strange is happening to the temperature along that main trail.
And this is the central mystery of the second clue. I mean, think about it. As particles stream away from the pulsar, they should cool down, right? They should lose energy, but they're not. Observations show that the farther you get from the pulsar along its tail, the hotter, the more energetic the X-rays become. How is that even possible?
This phenomenon is called spectral hardening, and it's the exact opposite of what you'd expect.
It's kind of like the exhaust from a car getting hotter the further it gets from the tailpipe. It just doesn't make sense. It suggests some unknown force is pumping energy back into these particles, re-accelerating them long after they left their source. The main idea right now is something called magnetic reconnection, where tangled magnetic fields just snap and release this explosive energy.
So, we've got an uncertain origin and a bizarrely superheated trail, but this final clue, this might be the strangest of all. It's a message broadcast directly from the pulsar itself in the form of radio waves.
Okay, so this pulsar sends out a main radio pulse and a weaker interpulse. You can think of it like a heartbeat. Thump, 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 thump. While using a really powerful radio telescope, astronomers found this bizarre pattern connecting the two. It's like a two-step dance. Step 1. If the small thump, the interpulse, is strong, then the big thump that came right before it was weak. They're opposites. Then, step 2. That strong little thump causes the next big thump to also be strong, but with a one-beat delay. It's this intricate, connected pattern, and we have absolutely no idea what's causing it.
And this isn't just a little odd, it's a fundamental puzzle. Don't just take my word for it. The research team themselves put it like this. This behavior is, quote, a conundrum for pulsar theories and cannot be satisfactorily explained by the current pulsar models. Our suspect is sending a coded message that our best physics just can't decipher yet.
So, after going through all the evidence, where does that leave our investigation into this cosmic fugitive? Well, we've learned a lot, but in a lot of ways, the case has only gotten stranger.
We're left with 3 huge, profound mysteries. We still don't know for sure where it came from. We can't explain what's reheating its trail against all known physics, and we can't decode the bizarre, phase-locked radio message it's constantly broadcasting. Every clue we found has only deepened the enigma.
But there is one final, absolutely incredible twist to this whole story. Our cosmic fugitive isn't just a mystery, it's a landmark. PSR B1929+10 is one of the 14 pulsars whose unique pulse rates were etched onto the golden plaques of the Pioneer and Voyager spacecraft. It's part of a map designed to lead an alien civilization back to our solar system. We chose this pulsar to help identify our place in the cosmos. So this object, a key to our own cosmic address, is still hiding so many of its own secrets. The case of PSR B1929+10 is not closed. Not by a long shot. It's an active investigation happening right here in our galactic neighborhood. And it just makes you wonder, what other secrets is it waiting to reveal?